In our AP Physics 1 class, we recently did an investigation looking at simple explosions where we had two cars at rest push off each other and fly apart in opposite directions. And we changed the mass of each car relative to one another. So some of the cars had the same mass and they went off at the same velocity. Other times, one car had a larger mass and it had a smaller velocity. So the mass ratios were different and it caused different velocity ratios. We actually found out something pretty interesting. Regardless of what the mass ratios were and the velocity ratios were, there was something the same about each car after each of the explosions. So here's an example. When you had a car that was twice as massive as another car, so 2 kilograms versus 1 kilogram, it was moving away from the explosion at half the speed as the other car. And what we said was the same was the product of the mass and the velocity. So here, mass times velocity, that's 2 kilogram meters per second. This one, mass times velocity, that's still, well, in this case, negative 2 kilogram meters per second. So the magnitude or the size of this value, the product of its mass and its velocity, which we called the momentum, was the same for each of the cars. So at least in an explosion, there's something special about this quantity of an object's mass and its velocity, which we call in physics momentum. In this video, I want to talk about what changes the momentum of a system. So each car in this case started with no velocity, so each had zero momentum, 0 kilogram meters per second. And after the explosion, they each had some amount of momentum. This blue car had positive 2 kilogram meters per second of momentum, and the red car had negative 2 kilogram meters per second. So what causes the cars to change momentum? Well, what causes anything to change its velocity, which would therefore change its momentum? Forces do. So in this video, I'm going to look at the quantitative relationship between the size of a force an object or a system feels and how much that object or system will change momentum. So to do that, we're going to use one equation that we use a lot in this class, which is Newton's second law. Acceleration equals the sum of the forces over the mass of an object or a system, and our new definition of this thing we call momentum. So we use a lowercase p for that, and it's calculated by taking the mass of an object times its velocity, kilograms times meters per second. So let's start with Newton's second law. And I'm going to expand Newton's second law by using our definition of acceleration. Because remember, acceleration is how much something changes its velocity for each and every second. The units are meters per second for each second. So we're going to turn A into delta V over delta T. We're going to use the right side of our equation on our AP Physics 1 equation sheet, where it's the net force on the system, or the object, divided by the object's mass, or the system's mass. And so I'm going to combine these. I'm going to cross multiply, so we can get mass times change in velocity on one side, and then force times change in time on the other side of the equation. So we're just going to simplify a little bit. So we get the mass of an object times its change in velocity is equal to the net force the object feels multiplied by the time it feels that force. So we're kind of thinking about a slightly simpler situation where we just have a constant force applied to something, and that thing starts at rest and it gains some final velocity. Let's assume friction is negligible, and so it's going to gain some momentum. So if we know the size of the net force on the object, how much will its momentum change? Its p change. So we've got this equation. So let's expand our delta v. That's the change in velocity. So the change in velocity is final velocity minus initial velocity. Now I'm going to just do some things to the left side of this equation. I'm going to distribute the m. So on the left side, we get the mass times the final velocity minus the mass times the initial velocity. And here we have m times v, a mass times a velocity. And what is that? That's our definition of momentum. So the object's mass times its final velocity is its final momentum, or its momentum at some final position. The mass times the initial velocity would be the initial momentum of the object. And here we have the final momentum minus the initial momentum. Final something minus initial something, that's the change in that something. So the left side of this equation is just the change in momentum of the object. And so here we get almost our final equation. We can quantitatively predict how much the momentum of an object will change just by taking the size of the external net force that it feels. It has to be outside of the system, or so in this case, the box is feeling a force from the person. That's an external force. If we take that force in newtons and we multiply it by the time it feels that force in seconds, that's going to give us units of Newton seconds. That will tell us exactly how much the momentum will change in units of kilograms times meters per second. In physics, we call the product of a force felt on an object by the time it feels that object, we call that the impulse. And the symbol we use to represent impulse is just an uppercase J. So the impulse is what changes the momentum of the system, or the product of a force times time is what gives us the momentum change. So on the AP Physics 1 equation sheet, this is an equation we now have that allows us to remember what changes the momentum of a system. And this is called our impulse equation. Now, if you look at the AP Physics 1 equation sheet, it looks exactly like this, except they don't use net force. They actually say it's the average force felt multiplied by time. And a little bit later in the video, we'll talk about why they use average force, not necessarily just net force. But before we're done with this, I want to look at the units. So if we multiply force times the time, does that really give us units of momentum, which is kilogram times meters per second? So let's look at the units together. If we have Newton seconds, remember a Newton is the same thing as a kilogram times a meter over second squared, a mass times an acceleration unit. That just comes from Newton's second law. So if we take this times seconds, notice we get the seconds up here, cancels one of them down there, and what's left over is kilograms times meters per second. It's a mass unit times a velocity unit. That does give us some change in momentum unit if we take a force multiplied by a time. So if you look at your AP Physics 1 equation sheet, the momentum equations we now have are in the lower left-hand corner. One is just the definition of momentum. Momentum is the mass of an object times its velocity. We just derived our impulse equation, which is J, or the impulse, is defined as the product of the average force on an object multiplied by the time it feels that force. And if we get that number, that gives us how much the momentum will change over that amount of time. And this other equation right here looks a little bit different than what we just saw, but it's just a slightly different rearranged form of using Newton's second law and our definition of momentum. So if we look back at Newton's second law over here, where we take acceleration as the net force divided by the mass, if we move the mass of the system over here, we get the net force is equal to the mass of a system times its acceleration. And acceleration, like we said, is just change in velocity over change in time. So it's mass times change in velocity over change in time. And if we group these two things together, mass times change in velocity, that's the same as how much something's momentum will change. So this version of Newton's second law, and using our definition of momentum, we can see that the size of the net force something feels will give us how much something's momentum will change over time. And if you look at it, it's just a rearranged form of our impulse equation that we just derived. Let's see if we can experimentally verify that the product of the force an object feels and the time it feels that force is quantitatively the same as the value of its change in momentum. To do this, we're going to make a 1 kilogram low-friction cart collide with a rigid wall. We will start by using the integrated spring as a cushion during the collision to increase the time the cart makes contact with the wall. A force sensor will be used to measure the size of the force the car experiences during the collision, and a motion detector will be used to measure the cart's change in velocity before and after the collision. So here's what the data shows. You can see that the force sensor is measuring a maximum of 6 newtons during the impact over a little between 0.2 and 0.3 of a second the impact lasted. And we want to figure out, does the product of a force times time, is that quantitatively the same as the change in momentum of the system? Well, the question is, what force would we use over what time? It felt a maximum force of about 6 newtons over about 0.3 of a second, but we can't just take 6 newtons times 2 or 0.3 of a second, because the force the cart felt was apparently not a constant force. That was only the maximum force, not the average force that was felt. So how do we find the product of force and time if the force on an object is changing? Well, it's really similar to how we found the amount of work done on a system or an object when the force the system was feeling was changing as it was moving. Remember, our definition of work, the energy added or removed from a system is equal to the product of force times distance. And if they're not parallel, we have to use the cosine of theta. But if we had a force versus position graph, and the force was changing. It was starting out at some value and gradually decreased to zero. We found the work by taking the area of a force versus position graph. And this is just a big general idea. If you have any graph, y versus x, the area of that graph is always y times x. So if we have a force versus position graph, the area of that will be the product of force times position, or force times distance. We also did this all the way back in Unit 1, where we were talking about graphically finding the displacement of an object by using a velocity versus time graph. And if the velocity is constant, the displacement of an object is just the velocity it's moving at times the time. But what if the velocity is changing? Like, let's say we have acceleration, so it's something's increasing speed while moving in the positive direction. Well, displacement is still the product of something's velocity and time, but if the velocity is not constant, we can't just simply multiply two numbers. So we want velocity times time, so we need to make a velocity versus time graph, and the area under that graph will be the product of velocity times time, which is displacement, which is why on a velocity graph, the area represents the change in position or displacement of the object. So let's go back to impulse. How did we define the impulse on a system, which tells us how much our momentum changes? It's the product of the force the system feels multiplied by time. Well, this would be a stereotypical graph of the force felt during an impact. While an object is impacting a surface over some amount of time, as it's impacting, the force increases, and then as it speeds up away from the surface, the force decreases. And so we get something that looks like this. Well, we can't just take a force times time. It reaches some maximum value, but it's constantly changing. And so if we want the product of force times time, we need a force versus time graph, and the area under that graph will be the product of those two things. So the way that we find impulse graphically is by looking at the area of a force versus time graph. So we'd shade all this purple area in, and all of this right here would be the amount of impulse on the system, which is how much the system will change momentum. So just real quick, if we have some impact time of t, and it reaches some maximum force, the area on the left would be 1/2 times the base, which is half the impact time, multiplied by the height of our triangle, which is the maximum force. And then this right side would be the same area. It's 1/2 base, which is also half of the impact time, 0.5 t, times the size of the maximum force. So we add those two things together, we get 0.25 t times the max force, that's this area, plus the same area. We end up getting that this expression is 0.5 times t times the maximum force. This would be a symbolic expression which represents the impulse on an object, which is how much the momentum will change. Well, let's look at this a little bit closer. We could take 0.5 times the time, or 0.5 times the maximum force. So I'll just rearrange it like this. So the impulse is half of the maximum force multiplied by time. If we look back at this graph, the maximum force is the biggest force it feels during the impact. And what's half of that value? Turns out, if the velocity is changing linearly like this, up and down, half of the maximum force is just the average value of the force experienced over that whole collision. And so this is why in the AP Physics 1 equation sheet, impulse is not just net force times time, it's average force times time. So whether the force is constant, then you just put in one number, or if the force is changing, as long as you know the average force the object experiences over the time, you take that average force multiplied by time, that is the impulse experienced by the system, which gives us how much the momentum will change. So if we want the product of force times time, we just need a force versus time graph, which we have, and it turns out that the area on a force versus time graph gives you the product of force and time, which we defined as impulse. So using our graphical analysis software, we found the integral, which is just another word for area, between the force that was plotted and the zero force. And so this shaded in red region right here is the area that has a value of negative 0.7828 second newtons, or Newton seconds. So that shaded area right there is the product of the force the car experienced multiplied by the time it experienced that force, even though we have a changing force. So it turns out that was about negative 0.78 Newton seconds. So that's the impulse the cart felt. So now the question is, what is the change in momentum of the car? Well, we use our motion detector to plot how the velocity changed over time. Here we can see the cart was moving to the right with velocity of positive 0.4 meters per second. And then the velocity went to 0, and then the velocity got negative, so it sped up in the negative direction to negative 0.35 meters per second. So in this gray region, this is the area where the velocity changed and the momentum changed during the impact. Well, to calculate the change in momentum from our velocity versus time graph, change in momentum is final momentum minus initial momentum, which is mass times final velocity minus mass times initial velocity. And if we group our velocities, we get mass times final velocity minus initial velocity, which is the change in velocity. So the change in momentum is mass times change in velocity. The car had a mass of approximately 1 kilogram, and the car went from 0.4 meters per second down to negative 0.35 meters per second. So the change was negative 0.75 meters per second. When we multiply the mass times the change in velocity, we can see that the change in momentum is equal to negative 0.75 kilogram meters per second. And when we compare that to the impulse, that's really close, within 0.03 of a kilogram meter per second or Newton per second. So we can see that experimentally, the product of force times time that an object feels is quantitatively equivalent to how much its momentum will change in kilogram meters per second. Now we'll see what happens when the cart collides with our rigid wall without the use of its integrated spring. So here's our data and a little bit of analysis. So we can see that the cart, it wasn't traveling nearly as fast initially. It was moving 0.23 meters per second. And when it came off of the wall, it was moving to the left at negative 0.16 meters per second. So its change in velocity wasn't quite as big. But look at our force versus time graph. That impact happened over a much shorter time, about 1/10 of a second or less. And the maximum force the cart felt was about 13 newtons. So over a small time, it felt a really big force, or a much larger force than the last example. When we look at the impulse, which remember is the area on our force versus time graph, that's the shaded red region right here, the impulse was negative 0.36 Newton seconds. And when we look at the change in momentum, the change in momentum is negative 0.39 kilogram meters per second. So now we have a second trial experimentally showing that the product of a force times time is pretty much the same as the object's change in momentum. When we look at both of our results, so this was collision number 1, using the spring to increase the time of collision. That impact, or that collision, happened over a long time, and the force was fairly small. So the change in momentum, you can change an object's momentum by using a small force over a long time, like in collision number 1, or we saw in the second collision where we didn't use the spring, that the car changes momentum with a large force over a small time. So both of these examples show that you can change an object's momentum with a small force over a long time, or cause the same change in momentum if you have a large force over a small time.